I'm a core developer at ChromaWay, and I work with the backend of the backend, the post-chain server. So we've seen a little bit before about what we have done, and it's a lot of new stuff. It's a new programming language, and with a pretty new syntax where we mix SQL and normal programming, like object-oriented programming. And we also define tables directly in the code. And this is a little bit new. And we also have Chromia, which is the platform where we want to create an environment for open data where you are supposed to be able to create your dapps and also share your data with other dapps and cross-pollinate an environment of open data, and also that you can have any mix of open data and closed data you like. So only the stuff that you define in RELL, it will be totally open data. You can also combine that with closed data if you want. So this is this presentation that I'm supposed to do now is about something that we're not gonna play around with in the later today in the demo. This is something that we just have finished coding and is in the testing phase and is soon going to be released. But this is one important feature for this platform, Chromia, when it comes to cross-pollination, where you can use data from other sources than your own. So dependencies, this is just a scheme of how dependencies can look in real life. This is libraries in Jetty, and you see there's heaps and heaps of libraries, and they depend on each other willy-nilly. But I'm not supposed to scare you guys. This is just to say that we already know dependencies and how it works. We can just apply this to our world, and it will be almost the same. So this what we're looking at here is the easiest case where we have two dapps deployed side by side without any interaction. So we have a bunch of nodes, group A, and a bunch of nodes, group B, and they are running their own dapps, and they don't really know or care about each other. And actually, this is very much like the blockchain world today with altcoins and so on. You can assume that group A here is, they are Bitcoin, and group B, they are Litecoin, and they don't really care. But they are both, in this case, they are both running in Chromia. So we're playing around with these nodes here just so you understand what's happening. So assuming that group B here they abandon their own Dapp, and they say, oh, we see that you guys running credit chain are so successful, we want to be part of this, and then they create relationship with everybody else, and they become block providers, and this community is flourishing and everybody happy. But we also support this kind of scenario where the group A nodes, they are producing data on this Dapp credit chain, while group B, they are just listening in and consuming the data. They are not allowed to build any blocks. And this is supported by PostChain today. But what we want to talk about is this situation where this group are having their own Dapp health chain, while also reading all the data in credit chain. And if we simplify the graph a little bit, we see that it's just two boxes with an arrow. So this is the dream scenario. It can't be simpler than this. It's like a simple dependency. But nothing is simple. So as soon as we open up these boxes, we see that it's not enough to define that one blockchain depends on another, we also need to know that every block here is dependent on a certain block, and everything lower than this in block height, but they don't know anything below. And it's not so hard to understand why this has to be a requirement, because say that you want to start up a new node, you want to start up a new health chain node, and it doesn't have any transaction or any blocks. So what they do is that they start from the beginning, they take block 0 and load all the transactions. And all these transactions, they are going to get processed, they're going to result in data in our tables and in the data that they store. So in that case, if we would have started this node by downloading all the blocks from this credit chain, when we process this transaction, they will know too much if they will start looking at the data from the latest block, and that might result in errors. So we want all the nodes to have the exact same status. So to become a little bit more practical here, we're going to look at one example where from the first chain we have a table called credit, and from the second chain, the health chain, we have a doctor's visit table. And when it comes to credit, we can see that if you get plus 100, that means that you have increased your credit with 100 and so on, and minus. And in this case, we can actually see the celebrities when they go to visit a doctor. And I don't think this is a very good example, really, because privacy issues and so on. We have like real names of Tom Waits when he went to the doctor. It might not be a good idea. But still, it's telling example about how this will work. So now we're going to have a competition. Lana Del Rey, when she goes to the doctor at this date, of the block height of health chain with block height 1, is she gonna have a positive credit? Is she gonna be credit worthy? Yes. And the way to check this is to see that block 1 of this chain is referring to height 1 on this chain, and then when you go down again, wrong way, you see that at this height it's referring to height 1, and at height 1 the only thing that has happened here is that Lana Del Rey get positive credit. But if we do the same thing for La Camilla at height 3, will she be credit worthy? And I already done the arrow for you here. Block 3 will refer to block 4 in the other chain in this dependency here. So that means that Camilla, if we know everything, we know all the data in block 4, we see that she already spent the credit, so she will have 0 credit and she will be rejected at the door. While if we haven't seen this, she would be accepted. So depending on what version, like these block dependencies are actually pretty precise in how they look at the data in different versions. And also, what I want to say is this only works if you never change your data, because the way that we process data here is sum everything that's relevant for a certain person, and we don't really change anything, we just add more. So how does it really look below the surface in post-chain? Well, we have a few tables, and it's not difficult. This is the only tables we have to support the structure. In post-chain, everything starts with a configuration file, and this configuration file is stored into this table. And during the life of a blockchain, we can actually change the configuration, and then it will say from height whatever, height 100, we will start using a new configuration. But we will only have one blockchain, so all the configurations, no matter if they change, there will just be one blockchain referred by chain ID. And one blockchain will have many blocks, of course, and one block will have, well, 0 or many transactions. And the dependencies are just stored in a table like this, that one block is dependent on another block from another chain. So that's how it works. And if we look at the RELL code, we have a specific keyword for talking about stuff that's not really ours. So we have the external, and the external is referring to the other chain. And then we define the class that's actually on another chain. And then we can start using it later on like it was our own class. But we can only read from it. And also, notice this keyword log, which means that this is an immutable table. It won't ever change, because if it was mutable, we couldn't really rely on it from a dependency point.
Can you use the keyword in your own database as well?
Yes. Yes. Log is for everything. So it's actually done now, but I wanted to add one more thing. So what I showed now is the simplest form of dependencies, just read something from somebody else. Even that is hard, even though it's so simple. But what we're doing right now, and is semi-complete, is how to transfer data from one blockchain to another. And to do that, you really have to prove that you have destroyed a certain asset on one blockchain to be able to recreate it on another one. And to prove that, you have to have proofs. And we have done a lot of different Merkle proofs, rather advanced Merkle proofs, to be able to guarantee this. And also, like, there is, okay, I don't know if maybe this is another presentation, but there is another chain that's oversees any transaction that is cross-blockchain, where you actually destroy data on one side and recreate it on the other. So that's something that's later anchored on in the big chains and so on. But this is what we're working on right now, and that's going to be released somewhere in the future. So yeah, thank you.